In this video, we'll examine how to solve a new type of differential equation called a separable differential equation. We've already seen how to solve a differential equation of the type, say, dy dx equals 3x squared plus 5x. And we might even have an initial condition to go along with this, say y of 1 equals 2. Here we just need to find an antiderivative of 3x squared plus 5x. So y would equal x cubed plus 5 halves x squared plus some constant c. Now we can use the initial condition. Say that 2 equals 1 plus 5 halves plus c, so that c equals negative 3 halves. Putting this all together, a solution to this initial value problem would be y equals x cubed plus 5 halves x squared minus 3 halves. We can check by taking a derivative that it satisfies our original differential equation, and we can check that it satisfies our initial condition. Now let's look at an example of a differential equation that is not of the type dy dx equals a function of x. Here we have a function of y. One thing that we might try here is to get all of the y's on one side and all of the x's on the other. So let's divide by y. In order to do this, we need to make the assumption that y is not equal to 0. Now, let's integrate both sides with respect to x. The integral on the right side is easy, but what about this integral on the left side? Looking at 1 over y dy dx, this looks like the result of a chain rule. The derivative with respect to x of some function would give us the result 1 over y dy dx. On the other side, we get x plus c. So what would this function be? Well, an antiderivative of 1 over y would be natural log of absolute value y, and then we'd have some constant k here, equals x plus c. By differentiating, we can double check that the derivative of this side would be 1 over y dy dx, which is what we originally had here. Now we could also move the k to the other side, so that we get this, and we could call this new constant, say, c1, some other constant. In the future, this will always be true, and we will not bother putting a constant of integration on the left-hand side because we'll always be able to move it over and combine it with the constant of integration on the right-hand side. We'll see that in a future example. Now, I'd probably like to solve this equation for y. So to do so, let's exponentiate both sides. So we get absolute value of y because the exponential function and the natural log function are inverses of each other. And on this side, I could write it as e to the x times e to the c1. To get rid of the absolute value signs, I could write y equals plus or minus e to the c1 and then times e to the x. Now, e to the c1 can be any positive number with the right choice of c1. Plus or minus e to the c1 could be any positive number or any negative number. The only number I can't get here as my constant in front of e to the x would be 0. So we could say that a general solution here appears to be y equals a e to the cx as long as a is not 0. But we made an assumption at the very beginning of the problem that y is not 0. What if y equals 0? If y equals 0, the derivative of 0 is 0, and we have 0 equals 0, and that satisfies our original differential equation. So y equals 0, in other words, if I let a equal 0 down here, would also be a solution. So we could say that this is our general solution, or y equals 0, but we could just put this together and say y equals b e to the x, where b is any constant at all, and this would be our most general solution. If we had an initial condition, say we knew that y of 0 equals 5, then we could put this information into our equation and see that b has to equal 5, so a solution to this initial value problem would be y equals 5 e to the x. Let's look at another example of the separable method where we're separating the variables, getting y's on one side and x's on the other. Let's start with the differential equation dy dx equals x over y. And let's have an initial condition, y of 1 equals 10. First, let's separate the variables. Here I'm going to multiply both sides by y. In general, once we develop this method, it's easier to work with differential notation, where we rewrite this as y dy equals x dx. Now, dy dx is not really a fraction, and you've been told since the beginning of differential calculus that you really shouldn't do this, but then we look at differentials and we say, well, maybe sometimes we can do this, and in this case it's useful. And now I will simply integrate both sides. So I get 1/2 y squared equals 1/2 x squared plus some constant. Multiplying both sides by 2, I get y squared equals x squared plus 2c, or I could call that 2c some other constant k. I could continue solving for y and then figure out what k needs to be in order to satisfy my initial value here, but we could also do that at this stage. If I plug in 10 for y and 1 for x, k has to equal 100 minus 1, so 99. Putting that back in, we get that y squared is x squared plus 99, and now we can solve for y and get that y equals plus or minus the square root of x squared plus 99. But we know that y of 1 has to equal positive 10, so the minus sign isn't going to work here. We only need the plus sign. So instead we can write as our solution to this initial value problem, y equals the square root of x squared plus 99. In general, if you have a differential equation where you can separate the variables, do so, integrate both sides, and then solve for y, or whatever the output variable is, to get your general solution, or if you have an initial value, use that to find a particular solution to your initial value problem.